Okay. Now we are back to the question. So let's start very general. Very general approach to understand quantum mechanics. With surface is really to look at the energies. We have to assign something to potential energy. We have to assign something to kinetic energy, and then we need to quantize this. And this approach is called surface quantization. I'm not going to explain to you in deeper way. It has been introduced already many years ago, and just formally. But this formal introduction of the surface quantization was very long time debatable. It was very true or not until really quantum effects were observed in surface. The idea is very simple. Suppose you have the simplest circuit, which has no dissipation. Ideally, we have just capacitor, and you have an inductor. So we have LC tank circuit. If there's a capacitor, then this charge will induce the current. So this electric field which you have there will induce the current flowing through the inductor, and then in the next quarter period, you need maximum current flowing through this inductor, and then the charge of the capacitance will reverse, and then the current will flow back in the next half period through the inductor. So you have something like potential and kinetic energy. Actually, to advertise one can produce this in different ways. So naturally, we think this is potential energy, this is kinetic. So in certain quantization is taken the other way around, but it doesn't change it. So the energy consists of the energy in the capacitor and energy in the inductor. And one can introduce simply the Hamiltonian, which is written there, which will be square of charge operator divided by twice capacitance and square of flux operator divided by twice inductor. Flux is basically some flux associated with magnetic field induced by this inductor. And it turns out, similarly to what we have in mechanics, where we have uncertainty between coordinate and momentum, here we have again the uncertainty between charge and flux. And this uncertainty means that these operators did not commute. So if you go to the commutation of the charge operator and flux operator is not zero, it's IH. So that means that actually we cannot determine with arbitrary accuracy the charge, and we cannot at the same time determine with arbitrary accuracy the flux. So this is quantum mechanically very general, but in a way it's describing here this quantum mechanical description describes harmonic oscillator, because these are all both linear elements, and the energy of the system is given by this parabolic profile. This can be charge, it can be flux, it's still parabola. And then if you can quantize the system, we have quantized energy levels, which are all equidistant. Now, remember what we need for quantum computing. For quantum computing, we need two-level systems. It means that we need to have two levels with some energy separation, which is unique, which is not coinciding with energy level separations to other levels. The reason is very simple. If you want to control the two states by, for example, using external magnetic field or by sending photons and this energy to the system, then you don't want to excite high states. So if you radiate this by magnetic radiation, then you of course will occupy all high states. And in a way, if you use the classical radiation, then simply you get a coherent state of the oscillator, and there is nothing interesting in getting any feedback. So to be able to change this potential profile to something different from parabola, one needs to make it unharmonic. And simply here, one can replace this inductance by a Josephson junction. So the Josephson junction is in a way a nonlinear impact. The reason I will explain to you in the next slide. This already you know. I explained this to you the previous hour. This you also know. But now let us do a simple thing. Let us take a time derivative of this equation. So dis over dt is equal to IC times cosine phi times d phi over dt. Okay? Now, this d phi over dt, which we get with differentiation, we simply substitute here by that, which is proportional to the voltage. And we see that the time derivative of the current is proportional to the voltage. And the coefficient of proportionality is given by this coefficient, but it will be not assigned at the differentiation to the cosine. So basically, this is corresponds to the definition of the inductance. Inductance is a dynamic electric circuit notation, which is manifesting something where the voltage is proportional to the time derivative of the current. And this is simply this value. So the inductance of the Josephson junction is flux quantum divided by 2 pi critical current divided by cosine phi. So this inductance is minimal if the phi is equal to 0. If the phi is increasing, for example, you increase the current here closer to critical current, then at the critical current, this argument becomes pi over 2, and cosine is 0. So this inductance basically diverges if you approach the critical current. If you approach the angle of phi equal to almost 2 pi. But we never approach exactly 2 pi because there will be populations, and actually this will never become infinite. But nevertheless, if you now put, instead of the linear inductor, if you put now this nonlinear inductor, then light changes. Instead of this situation, which again is harmonic oscillator, LC circuit with parabolic potential and equidistant energy levels, as a function of phi here, which is associated with the current flow of the inductor, if you put down the Josephson junction here, then the potential becomes like this. This potential is the softly unharmonic potential because it becomes it's limited here. So the energy level separation between 0 and 1 is going to be the largest, and then the next energy level separation between 1 and 2 is a little smaller. This is a little more smaller. This is more smaller, and so forth until we empty all the until we count all the levels. Now, if you want to read the systematic introduction, I recommend this this review. I will put it also in the shared files, and that's a really very basic introduction into quantum circuits. So this circuit is historically called transmode. We will discuss it also in the lecture course, but not today. They will start from very basic things. But in a way, transmode by itself is very simple. Simply replace this inductor by that inductor, and you get not this potential, but that potential. So this is all rather straightforward. As this transmode, you're getting a harmonic oscillator, and it's also convenient instead of a single Josephson junction, which we use here. Remember, here we have a single Josephson junction. This is now we can split this Josephson junction in two. We can make a DC square, which I explained briefly in the previous lectures. And if you apply magnetic flux, then you simply can change the amplitude of this potential. So you simply change the amplitude of the potential by changing magnetic flux because you modulate the critical current of the whole junction. Now you basically have here you have another wire which is going to capacitor, and then this wire goes there. So instead of single junction, you have two, and you control the height of the potential by applying the external magnetic field. And then these are the energy levels of this transmode. This is a 0-1 transition. This is 1-2 transition. You see, and harmonicity is quite appreciable. It's few percent, which is quite good. Now let's look into this story from one general perspective. Josephson junction introduces for us unharmonic potential. What I told you before, the potential is this cosine, right? So in a way, if I have not, if I change the phase difference by 2 pi, then I go to the next minimum of the potential. So this is simply a cosine function, which is lying in the flat surface. Right? So it's a horizontal cosine function, which is this potential. However, if I apply a current on the junction, what I'm doing, I'm tilting the potential. So I'm doing simply the work, and the potential then, which is written here, is including already cosine and the the tilt, which comes from the current equation of the pendulum. This potential is also the same for pendulum. Remember, if I write the equation for the pendulum, then at zero torque, this state has the same energy as this state. However, if I apply some torque, then by doing rotation, I do some work, and basically the next minimum will be a little lower. And larger is the torque, larger is the speed. So very similarly here, this slope is determined by the torque for the pendulum, or for junction is determined by the current. And then one can generally write, look at this even more abstract. I told you analogy between the Josephson junction and the pendulum, but now let's talk about yet another analogy. We have now cosine potential, which is like this. When we apply current or torque, this potential becomes tilted. It's a famous tilted washboard potential. Потенциал стиральной доски. Древние времена на таких досках стирали. So now imagine that we have a virtual particle, which is our system, sitting in the minimum of this potential. As I told, if there is no torque, then this minimum is equivalent to that minimum. But now I start applying torque, so in the picture of pendulum, my angle changes. I'm suddenly here, so I have very shallow potential, and the pendulum will start rotating once this local minimum disappears. Disappears, of course, at the same time when all other minima disappear. So I can think about my system as a particle which is sitting in this washboard potential. And then when potential is tilted, it becomes very shallow, it becomes very unharmonic. So the particle will be, of course, behaving here according to the laws of classical physics. But if we describe everything by quantum mechanics, it will be can be also described as a quantum particle. And the idea goes back to 1980, where famous physicist Tony Leggett, who got his Nobel Prize together with Ginsburg and Brikosov for something else. He came up with the idea that actually one can think of this virtual particle here as a quantum particle. One can simply quantize the states of the particle, state of the particle in the potential. One gets here harmonic energy levels. And with this logic, the equivalent mass of the particle is proportional to the capacitance of the junction. I told you already, the capacitance is associated with inertia. So if I make a junction which will have a very tiny capacitance, then this effective particle becomes very, very light. And if it becomes light, then quantum mechanics starts playing a role. And if one puts the numbers here for small capacity junction, then the effective mass of this particle is actually ridiculously small. It's several orders of magnitude smaller than the mass of free electrons. Single free electron. So you have something macroscopic, you have the circuit, which is macroscopic. But the equivalent inertia of the circuit is so tiny, dissipation is very small. So inertia is extremely small, so that the whole circuit described by this variable phase difference on the junction is behaving as a quantum object. Look, something like maybe 30 years, this was sounding like nonsense. And people observed first quantum effects in this paper in '87, only observing quantum tunneling of a particle across this barrier here, but never never observing any coherent dynamics. Actually, in this work, they were able to observe energy levels in this potential. Very same people who are now leaders in the field of superconducting quantum computing. Yeah. I had the pleasure to spend my sabbatical with John Clark and UC Berkeley. These guys are now not less famous as John. Is one of the fathers of screen, basically.
So, здесь мы эквидистанты, да? Поскольку потенциал не ангармоничный, у нас не эквидистант.
Да, именно поэтому, потому что мы делаем очень сильный наклон, и когда потенциал очень сильно неангармоничен. Он задается полиномом третьего порядка. И поэтому это расстояние очень сильно отличается от расстояния. Даже больше, чем, например, ровно косинус. Anyway, so Tony Leggett actually predicted that there will be energy levels of the system and this potential. Moreover, he predicted that there will be tunneling across this barrier if the potential is very shallow and this barrier is very low. And there was also a discussion if one could observe time coherence of the quantum states. For example, if one one can ask the question: can one prepare a superposition of the state of the particle here and there? Can one prepare a superposition of the two states? And this was all really questioned and never answered. And then the answer came from the work of John Martinez exactly 20 years ago. And the idea is, of course, the following. So now let's think about what should be the conditions to observe. These energy levels are very small distance. So the distance is in the range of microelectron volts. So if you convert microelectron volts divided by this energy by Planck's constant, you get a frequency of about a few gigahertz. Now let's think, what is the frequency of few gigahertz? So to be able to prepare the system on the ground state, the energy level separation between the ground state and the first excited state, H bar omega, has to be larger than thermal fluctuations. Thermal fluctuations have the energy scale of kT or kBT, Boltzmann constant times temperature. So if I divide this H bar omega by Boltzmann constant, I get the temperature when these levels get mixed by thermal excitations. And if you take the frequency of 10 gigahertz, which will be rather typical for this surface, then it will correspond to the temperature of about half Kelvin. So in these units, 1 gigahertz costs 50 millikelvin. If you want to work at 10 gigahertz, you have to be 10 times lower in temperature than that, which means like about 50 millikelvin or less. That means, this explains why aluminum is the material of choice. Simply because you don't need any high temperature superconductor. You don't need niobium. This aluminum itself, which has a gap of about 1.2 Kelvin, will be excellent superconductor at 50 millikelvin, because most of the electron excitations will be frozen there. Most of the particles will be frozen. In reality, it's different, but that's the expectation. So we have to cool down to temperatures about 50 millikelvin or below to be able to see individual energy levels separated by frequencies of about 10 gigahertz. That's why one can use, or one has to use a very special technique to achieve these temperatures. And this technique is called helium-3, helium-4 dilution refrigeration. So I told you about helium-4 in the beginning. Cameron Cordes 100 years ago, more than 100 years ago, achieved temperatures of 4.2 Kelvin. Actually, he achieved temperatures lower by pumping helium. So if you pump the vapor of helium above the surface of helium, then the temperature of helium gas goes down. And if you pump very, very hard, then you maybe achieve temperatures of maybe like 1 or maybe 0.9 Kelvin. And they don't go much farther. If you use helium-3, pure helium-3, you can do the same thing. So it's a different isotope, lighter isotope of helium. And it allows pumping of helium-3, makes it possible to achieve temperatures about 260 millikelvin. However, if you make a mixture of helium-3 and helium-4, typically about 10 to 15% of helium-3 in helium-4, then one can use the so-called dilution principle. And the idea is that you condense this mixture in the so-called mixing chamber. And then you have naturally the helium liquid of this mixture is such that it forms two phases. One phase is dilute phase, where there will be less atoms of helium-3, and there will be also the rich phase, where there will be mostly helium-3 and less helium. And when atoms of helium-3 go through the surface between two liquids, they actually give a lot of, they take away a lot of energy. So the enthalpy of this crossing process is very, very high. And actually it makes possible basically to achieve your temperatures down to almost 10 millikelvin or even less, depending on the strength of your pump. So what you do, you have closed cycle here, where you have your mixture, helium-3 and helium-4. You pump this mixture from this mixing chamber through the tube, which is connected to the heat exchanger. So basically, outcoming liquid cools the incoming liquid here. And then you compress this mixture, and then by compression and expansion in the free space, you know that you have this adiabatic expansion. This is the simplest process of achieving the cooling principle. And then basically the pump helium-3 goes. I think I started explaining the wrong way. This is the way it goes out. This is the steam, and then helium-3 gas, which evaporates from the surface, goes back, and then it's pumped. And this is a very thin capillary. And you know that if you have a capillary, then it's almost like expansion in the open space on the other side. So and then there is exchange between helium-3, which is incoming here, and the cold helium-3, which is coming out. So basically, by having several stages, this is about 1 Kelvin. This is less about than Kelvin, and this is the Nixon chamber. By doing this process, you can basically achieve here temperatures around 10 to 20 million. So these machines are quite expensive, but they can be routinely made, and we have a number of them here in Moscow. The favorite one is the machine which is made by a company Luforce, the Finnish company. At VCs, when you go to the experiment, you see 2 of these machines. There is another one in the lab of Aleka Stachik. Well, it costs about 300K, actually more now, but it's just refrigerated, so it's not really something fancy. There are thousands and thousands made. I heard that last year, 2 years ago, China was ordering 200 of these refrigerators from Lufthansa, over to their labs in China. So this technique is a bit special, also for the reason that helium-3 is quite expensive. So it's produced in nuclear reactions, and the favorite source of liquid helium was actually the hydrogen bombs, which were decaying with time, and then decay of tritium leads to formation of helium-3 gas. This was one of the strongest export resources of solar. Nowadays, the situation is probably different.
Вопрос.
Yes.
Почему люди используют разбавление промывки соли?
Прошу по-русски. Промывительные соли, действительно, это очень перспективная вещь, она позволяет достигать очень низкой температуры, но это процесс, который происходит как бы в одночасье, и потом вся система нагревается. Это время нагрева довольно небольшое, минуты или часы. То есть нельзя сделать эксперимент, который будет длиться сколько угодно. То есть для коротких измерений быстрых используют промывание соли, алифатическое разграничение. Но это не есть решение коротких шагов. Не работает. Okay, I think I need to start the next set of slides. All right, so it took me a little longer with the introduction, but I hope those people who haven't heard of the superconductivity at least had some guidelines how to approach it. Now, in the first lecture, we'll talk about phase qubits and flux qubits. I think charge qubit I will not manage today. It's the same stack of slides, but I need to rearrange them. This year, I decided really to go a little slower than a year ago, just to keep more people on board and really get better understanding for the sake of saving some material. So, let's keep it. The generic circuit for superconducting qubits, superconducting quantum bits, is this very simple circuit which consists basically of three elements. And it includes the Josephson junction here, which has its own capacitance and also its now known Josephson inductance. There is a capacitor in parallel. Generally, if you need to, for example, increase the capacitance of the circuit, you add extra capacitor here. And for many reasons, one can also may want here to have the inductor. Inductor is needed, for example, if you make a very large inductor, then very small potential fluctuations which occur due to the charge noise, which you already heard about when we talked about quantum dots. Charge noise is really the problem for many small size electronic devices. This charge noise impulse will be reduced if you have some leak of the charge, which will compensate for charge noise. And this generic circuit can be actually has been derived already after many qubits have been implemented. In the very beginning, 20 years ago, people were not really having this classification. But now, since one have looking back, having many different qubits, many different species of superconducting circuits, one can sort of classify them under the same umbrella under this type of circuit. Now, there are different types of qubits: charge qubit, phase qubit, flux qubit, transmon qubit, and so forth. And we'll talk about all of them. And they all correspond to different ratios of the energies. So here you have the Josephson energy, which is associated with the Josephson current. We'll talk about that. Now you also have a charging energy, which is basically the energy of charging this joint capacitor. This is C plus Cj, they are in parallel. So this capacitance can be either small or can be large. And this capacitance you charge by a charge of a single Cooper pair. And this energy scale is giving you another scale in the system. So there are different basically qubits based on different ratio. And there is also another energy, which is the energy of this inductance, which is flux quantum divided by 2L. And this is the characteristic quantum scale of the energy of the inductance. And this energy can be either zero if there is no inductance. This is the case for charge qubit or transmon qubit. But for flux qubit and for phase qubit, this energy EL is not zero. So once you have it here, then this process is not zero. So this is a very generic thing. It doesn't explain you anything, but it gives you like an overview that one can look into different directions of the parameter space. Talking about quantumness, when you make a quantum system, for example, mechanical quantum system, you can either decide yourself that you prefer to measure the coordinate, or you rather prefer to measure the momentum. And if you're prepared to measure the momentum very well, then coordinate becomes quantum mechanically largely fluctuating, and other way around. If you prefer to measure the coordinate, the momentum fluctuates. So it's basically playing with quantum games leaves a certain choice for you, which particular side of the uncertainty, quantum uncertainty, you prefer to take. And this is also a decision between convenience of using different types of superconducting qubits. This is the whole zoom of superconducting qubits, which we will discuss. It all started first with the charge qubit. The first experiment was made in 1999, Nature paper, which didn't get yet its Nobel Prize, but hopefully soon. This is the flux qubit, which started about the same time, but experimental implementation was a year later. And the phase qubit, which I already mentioned briefly, was yet another year. Now, after 20 years of evolution, and before that, there was a kind of boiling down of all of this type. Some of them were decided to be non-practical hardware, and the most favorite hardware are the so-called transmons. The transmon basically is a single Josephson junction, maybe a little squid, which is shunted by external capacitor. So this is the external capacitor is needed to make the transmon really convenient to operate and bring the frequency range in a convenient range of electronic devices. There is another qubit type which is called fluxonium or flux qubits, which kind of a derivative of that, which rapidly receives more and more attention. And that's where actually probably most things will happen in the next years, because there are currently only 3 groups around the world working systematically with that. One group is our group here in Moscow. There is a strong competition from Alibaba. They make their own Foxonium processor. And also excellent work done with the pioneer of these devices, Vlad Gончарян, who graduated from this tech back 15 years ago, and his PhD in Yale, and is currently working in Lausanne. Okay, first, very simple, just to give a bridge to what we discussed before we really go deep into the superconducting qubits of different types. Let's start from something we already know. You already know this tilted work potential. So I have this cosine, I have tilted by current, I have a very shallow minimum. This is my zoom in this potential. So there will be another minimum here, another minimum there, but there will be only a few levels there. Of course, these levels are not localized completely in this potential, because there is always probability of tunneling from here outside. But this probability is very low, exponentially low for lowest levels, and is of course higher than for high levels. In this very simple experiment, the very same John Martinez, who was a master student of John Clark back in the 80s, he was working at NIST at that time, and he made a very simple experiment. Instead of applying continuous wave microwaves, which they did that time to observe spectroscopy of the energy levels, they applied now microwave pulses. So like you do in magnetic resonance technique, when you apply classical radiation at the frequency of the transition between ground state and excited state, like we do it in the atom. What happens is that your system, under the effect of classical radiation, coherently evolves between the ground and excited states. And this frequency of evolution depends on the amplitude of that radiation. So this frequency of the evolution of the population is actually, these oscillations are called radio oscillations, which you know from atomic physics. And these radio oscillations, they bring the system in superposition of 2 states which are coupled by this radiation. Basically, what he was doing here was applying microwave pulses at the frequency of between 0 and 1 in a very similar way like people do with atoms, which we talked about in the first part of our course. And then the question was how to read out the system. And if you have a current bias Josephson junction, then having the particle localized in this potential means that there is no voltage, nothing there. But once the particle goes out of the potential, it appears on this side, and the next minimum is somewhere here. And when the particle gets down to this minimum, it gains so much kinetic energy that it cannot be stopped anymore. So it starts running down the potential. Now look, this axis is phi. Once you have now continuously changing phi as a function of time, you have d phi over dt non-zero, you have voltage. So basically the idea was very simple. Suppose we bias now our system at the ground state, and then we apply this microwave pulse of a given duration and excite the system from the ground state to the excited state. Our state should evolve between ground and excited. In a coherent fashion, we should perform radio oscillations. But now we didn't want to measure the radio oscillations. And the idea was just apply a particular duration of the pulse and then measure the population of the excited state. And then this population of the excited state was measured in a very simple fashion. Simply when the microwave pulse was over, there was a little peak, little kick of the current, so a little tilt of the potential over a short time. And then with this tilt, this value of the current, the lifetime of this state was exponentially shorter than the last lifetime of the ground state. And the system was simply tunneling out from the potential, and then the voltage was appearing. So if this pulse, the readout pulse, came in a moment when the system was in the excited state, there is a voltage. When you are in the ground state, then of course there is a no voltage. And this contrast was really quite large. It was almost a factor of 1,000 in the lifetime. So basically, if you are in the superposition, like state 0 plus 1 divided by square root of 2, then there will be 50% probability of measuring this voltage pulse. 50% probability of not measuring the voltage pulse. But if you're in the ground state, then of course probability will be 0. You will be always there. If you're in the fully excited state, probability will be 100%. You will always measure the transition to the voltage state. And basically, this type of measurements came with this very simple observation of radio oscillations. Okay, these are not data of John, but this is data from my group, done like 2 years later, but showing the same physics. If you go from below, now this horizontal axis is probability of measuring the excited state. So this is the appearance of the voltage after shock pulse of current. And here is 1, here is 0. And from below to up, you increase the amplitude of the microwave field. You increase the amplitude of the driving field. And as you see, the frequency of the radio oscillations increases. But also you see that these oscillations, they decay. So there is a decoherence. And basically, if you wait for like a fraction of microsecond, hundreds of nanoseconds, then the state is not there anymore. So you always measure 50% probability of 0 and 1. And that means actually that the system, after this time, basically forgets which state it started from. So the noise, the external influence of the circuit are such that this coherence time is really very, very short. And the most beautiful thing of this field was that over the first 10 years of the development of this very first qubits, they appeared in around the year 2000, as I said. After 10 years, the coherence time, which was measured to be about a nanosecond for very first qubits, this were not first qubits, this were a few hundreds of nanoseconds. But this coherence time actually increased by almost a factor of million. So nowadays, the coherence time of these qubits is in the range of milliseconds. And this became possible due to the understanding the physics of this coherence became possible due to the clever engineering of the microwave lines to avoid any unwanted interaction with the environment. And also a lot of material science, how to make more coherent qubits, but we'll talk about this later. All right, so let us discuss how to make the flux qubit better. The problem of phase qubit better. The problem of phase qubit and this very short coherence time was that the appearance of voltage, which was needed to detect the excited state, led to the dissipation. So once you have voltage, you have current. Current times voltage is the power which you dissipate in the circuit. And the problem is that thermal conductivity of all the materials at very low temperatures is very high. So if you generate very tiny power, then you heat up the temperature, the electronic temperature of your system very high. And then you're not anymore able to cool down your system in the ground. And to avoid this thing, the very same group, John Martinez came up with the idea to enclose the junction in a loop. Okay? So making a single Josephson junction, enclosing in a loop. And then instead of the initial potential, which was the cosine, which was tilted by current, now one can do it differently. The loop has certain inductance. Okay? So you have a junction which gives you the cosine, and then you have the inductance. You know, inductance depends on the parabolic way on the phase difference. So basically, you make a superposition of the cosine function and parabola. And if you modulate parabola with a cosine function, you will have something like this, and then some bumps in the bottom, and then again something like this. Parabola modulated by cosine. The amplitude of cosine is constant everywhere. And parabola goes on the sides very steeply if you go away from 0. So then by choosing the value of the steepness of the parabola, which is determined by the inductance, one can actually make it possible to have a well-defined number of energy minima in this potential. So to make the long story short, this flux which is entering into the energy has now the linear term determined by the external flux, and then the term associated with the Josephson junction. And this parabola, depending on the inductance of this loop here, this parabola can be either very soft. If the inductance is very large, then parabola is very, very soft, and there will be many bumps of cosine inside the medium of the parabola, so it will be many minima. Or it can be very steep. If the inductance of this loop is very small, then the parabola is very steep. And there will be something in between, something shown here by the green curve. And this corresponds to the parameter beta L, which is basically the product of the geometrical inductance of the loop times the critical current divided by the flux quantum. You can also recognize that actually flux quantum divided by critical current is the Josephson inductance. So they basically beta L is the ratio of geometrical inductance to the inductance of the junction, because it's just flipped around inductance of the junction. One can just write all this energy, one can calculate what's the profile, one can put here the external flux. The external flux will sort of move this minimum. So it will move this minimum to this point, this one will move up, and then one can nicely see what happens with this parabola if one changes the external flux. But one can easily make the situation such that there will be, similarly to the cosine potential, there will be few energy levels here, and then when the system tunnels out from the metastable state, it will not go all the way down like cosine did, but it will go down to the next minimum. So the phase only change by 2 pi. And then the task will be to distinguish between the phase difference given by this potential well and the phase difference given by that potential. And this is achieved by using the measurement squid, which can then be coupled to this device. So this device is the phase qubit, which is in fact RF squid or single junction squid, which I already mentioned earlier. And our desired situation will be that one can reflect this potential like that, then apply microwave coupled to 0 and 1. And then if you have the state 1, then this state will tunnel out in the deeper well. And if we are able to determine this well, distinguish this well from that well by measuring the flux in the loop, then we are able to do to measure this phase qubit. So this was introduced actually 2 years later after the first phase qubit was made. This is typical experiment. So this is a qubit. This is the measurement squid. Excuse me. This is the flux control. Sorry, this is flux control. This is the qubit. So with this basically control, we can make the potential. We can make this minimum deep and this minimum high. So we can manipulate this by this external flux. And then this is the measurement squid. If you want, you can think about why there are 3 junctions and not 2 junctions, but this is a very technical small detail, which makes the measurements a bit more convenient. What is important is that if you have the squid, and the squid measures the flux in this loop, and then if you go from this state to this state, this flux changes. One should be able to distinguish that state, which is called left, kind of counterclockwise current in the loop, and this state is called right. This is clockwise current in the loop. They are basically detected by this measurement squid. And there are 2 histograms here. This is the left state and this is the right state. And if one can discriminate between the 2 histograms, then one can basically determine the position of the system. And discrimination is also determined on the coupling coefficient between the squid. But if you couple the squid too strongly to the quantum system, then of course you also have the back action. So you will unavoidably introduce extra decoherence in the quantum circuit. And therefore, this coupling has to be kind of balanced such that the resolution is sufficient to distinguish the states, but the coupling is not that strong. Why? Because when the squid is coupled, then it's also coupled when the coherent evolution between 0 and 1 takes place. Of course, these measurements are destructive. So you prepare the quantum state, you prepare the superposition, and then you project this quantum state to the localized state, to the classical states. And by doing that, you destroy the quantum state. But you basically do this experiment over and over, and then you measure probabilities, and that's how quantum mechanical measurements are actually projecting measurements work. So you project to the localized states by doing destructive measurements, and then you measure, basically acquire many samples of data and obtain probabilities. This again the procedure. So first you apply, this is the flux in the squid, basically this flux, which you have there. Then this is the time. First you prepare the system in the deep well. Then you change the flux so that you go into the shallow well. So you rise this one, this goes up and this goes down, becomes deep. Then you make the potential very shallow, short-living, apply microwave, and then you also apply small DC pulses. Then if you are in the excited state, you tunnel out. If you're in the ground state, this pulse is too short to have sufficient probability of tunneling out. And then basically you freeze. And when you freeze, you have all the time of the universe to measure the result, because you already projected your quantum state to the localized state. If it tunneled out, it's in the deep well on the right. If it didn't tunnel out, it's in the deep well on the left. And then depending, then you send the current of the squid, and then you have different switching current of the squid. If you measure the smaller value, you have the state left. If you measure larger value, you're in the state right. So this is a very simple procedure which was initially used to measure quantum circuits. And this picture already showed, I think, maybe that one. So typical coherence times which were measured in the very beginning without using the junction in the squid were in the range of 2, 3, 5 nanoseconds. And by putting the junction in a loop, making the squid increase the times by or magnitude. So this was already data shown here with about hundreds of nanoseconds per coherence. And then by doing the different procedures which we discussed already previously, so you could apply, for example, the radio oscillations, and you apply, for example, half period of the radio oscillation pulse, and then you measure exponential decay of probability of the system to remain in the excited state. This will give you the time t1. And if you prepare a superposition of the state in equatorial plane, superposition half and half of 0 and 1, then you will stay in this state forever if there is no dephasing. But of course, there is always dephasing there, and this dephasing will lead to random diffusion of the state in the equatorial plane. And to measure this, people use the Ramsey procedure, which is applying pi over 2 pulse, and then waiting and applying another pi over 2 pulse, which will bring your system to the other side. And if you detune the frequency of the microwave from the resonance, then probability of coming into the state 0 and state 1 will oscillate in time. It's a so-called Ramsey oscillations. So you don't remember from atomic physics, please refresh that. And I will explain again, but just to sort of facilitate, I recommend that. And if you want to have, for example, compensation for the low frequency noise, then you use the so-called echo technique, where you use refocusing pulses, pi pulses between the 2 pi over 2 pulses. So,
почему затухание радиоосцилляции означает декомпилляцию?
Во время затухания радиоосцилляции существует формула, где фигурируют Т1 и Т2. В первую очередь затухание определяется Т1, и Т2 относится свой эффект. Если шум белый, то Т2 всегда ограничено Т1. То есть для обычной декодерной системы Т1 в 2 раза меньше, чем Т2. Если время релаксации какое-то есть, то Т2 не может быть больше, чем удвоенное время релаксации. Вот. Но это для обычного как бы, белого шума, для всякого другого шума не относится. Okay, we have like 20 minutes. I think I will take time to explain to you today the flux qubit, and then we'll discuss later on flux qubit. Yes. Flux qubit, and then we'll discuss later on the next one. Historically, chat qubit was before flux qubit, but of course, this is they're both important to understand the issue. So very generally, I told you about the uncertainty relation. And you know the Heisenberg uncertainty relation is a fundamental quantum uncertainty which limits the accuracy of quantum measurements. You cannot determine momentum and coordinate at the same time. Another example of uncertainty relation can be found in optics. If you have an optical fiber and you send light, then when you send many photons, you send a pulse, you send a wave packet there. Then you can measure the phase of this wave packet. Okay? But if you send a single photon, you know that it's a single photon, but you cannot measure the phase. So similarly, for light in a fiber, there is a certain relation between number of photons in the pulse and the phase of the pulse. And next step is also very similar. So in the superconductor, you have a similar certain relation between number of particles involved and the phase difference in the junction. And the idea is very simple. Suppose you have a big piece of superconductor, which is this green block. Then you have a tiny Josephson junction and a tiny grain of a superconductor. We need to do it if we need to make capacitance very small. Okay, so we want to make capacitance very small. We took a junction of the size maybe 30 nanometers by 30 nanometers, and we connected here a grain which will be roughly this size times this, or plus the thickness of the metal. This grain will contain many electrons. It will contain billions of electrons. Nevertheless, there will be a competing process. On one side, we want to transfer copper from the grain to the bulk superconductor, or another way, from the bulk to the grain. This is the Josephson effect. But to do this, we need to overcome the charging energy. The thing is that you cannot transfer less than one copper pair. You can only transfer 2 electrons. And this energy can be larger than the Josephson energy. In this case, the current, the supercurrent will not flow. Because the charging energy, it's a square of electron charge, strictly speaking, 2e, in parentheses, all square, but I just dropped this factor of 4. Charge square divided by twice the capacitance. This is the charging energy. If capacitance is very small, this energy is very large. Now, if capacitance is larger, then the energy which will dominate will be Josephson energy. And this energy is simply the critical current times the flux quantum divided by 2 pi. So large is the Josephson coupling, large is the critical current. And these two energies need to be compared. And now important, so looking back to this thing, when we say about the number of particles, this is the change of the particles from 100 millions to 100 million plus 1, and counting Cooper pairs. So this is delta N. And to do this, you need to overcome this energy, right? If this energy is large, then this process will not help you. So that means that if you want to determine the number of particles on the island very well, you will not be able to determine the phase. So the phase will strongly fluctuate. The Josephson effect will be suppressed by quantum fluctuations. And in opposite, if you make the capacitance large, you can have tunneling of Cooper pairs for free. The phase difference is fixed. But Cooper pairs are tunneling back and forth all the time. So the number of Cooper pairs is not fixed. And basically, then the Josephson energy dominates. And then depending where you are, you could either make the case that the charging energy is much larger. Then you have the charge cube. You can make this operate as a quantum circuit, which will be controlled by voltage, and correspondingly, quantum states will be states of charge. If you go another limit, make the superconducting islands large and extend it, and it turns out to be more convenient to close it in the loop, then the charging energy is much smaller than the Josephson energy. And the good variable, which is well determined, will be the phase difference, but fluctuating variable will be the number of particles in the island. And this is basically two limits. Like you make a momentum qubit and coordinate qubit. This is similar to mechanical uncertainty relation. So first we'll discuss today this one, and then next week we'll talk about that one. Okay. Let's see. You already know that we can make a system where a junction is included in the ring. And I told you that when you change the external flux, then you change the height of this to minimum, you move it up and down. Now, what happens if your flux, which you apply externally, is exactly half flux quantum? In this case, you have two minima, symmetric to minima, and the barrier between them. Of course, it depends on the inductance. The height of the barrier depends on the inductance. If the inductance of the loop is very small, there is no barrier. If the inductance of the loop is large, then there will be multiple minima and very high barrier. And then, but generally thinking of this, suppose you have now a barrier which is not very high. So then you have one state with the counterclockwise current, and this is the state with clockwise current. These are two macroscopic states with many electrons moving on each state. Question is, can you make really superposition of multi-particle state of many, many electrons? So you have one state with clockwise current when all of them are moving to the right, and then another state where they're all moving to the left. Then we'll make a superposition of the states. And I would tell you that 20 years ago, the answer was not obvious. So people were really searching for this answer. It was really almost weird to expect the quantum properties of that. Now we understand that all these electrons, their number don't matter because they're all in the same condensate. And it's not a state of individual electrons. They are all decoupled, those states. What we couple, we are coupling the states of superconducting condensate. And in this case, everything is simple and it works. Actually, that's how the nature is. So suppose you prepare the state in the left well, and you allow for tunneling to the right. In this case, of course, you will have a superposition of the two states. And then quantum mechanically, if you make a superposition, there will be a symmetric state and antisymmetric state. So the lowest energy will be symmetric state, and the antisymmetric state will be a little higher, described by these two wave functions. So this is the symmetric one, 0, and the green is antisymmetric 1. And the energy level separation between them, these are the eigen energy states, is actually proportional to the tunneling probability, proportional to the tunneling energy which is coupled into two states. So one can actually have those states as localized. One can use them, for example, for measurements. And this basis is the states which are actually already superposition states. One can tell the lowest energy state will be something like this, and the highest energy state is going to be something like this. So this is just a double low potential, and particle with double low potential is fusion. All right. So can we make this in a superconducting loop with a Josephson conjunction? The problem is that if you make now this thing with the flux qubit, which I explained, with the phase qubit, which I explained to you in the beginning, then the parameters are such that the height of this barrier between the two states is extremely high. So theoretically, one gets the splitting, but the splitting will be in the range of hertz. You cannot determine it because the barrier is too high and the probability is very small. So to be able to observe the superposition states, one needs to make this barrier very, very low, very, very tiny. And this requires very difficult, solving very difficult tasks. One needs to adjust the inductance of the loop very precisely with respect to the inductance of the junction, or other way around. Adjust the inductance of the junction very precisely with respect to the inductance of the loop. This will make it possible to move the barrier between those two states down, and then eventually drop it completely. So this will be then if you move this down, these two energy states will separate. The biggest problem was when you do this control of the Josephson inductance, you do it by basically replacing the junction in the squid and using another coil to control the flux of this loop. It was a very difficult experimental problem because any coil which you bring down to the circuit generates some noise. And this noise, of course, makes this barrier fluctuate. If the barrier fluctuates, there will be there will be very strong dephasing of the quantum state because of the fluctuating energy eigenstates under the effect of the forces in the environment. And this actually took 10 years of IBM team of Claudia Tesch from 1990 to 1998, I believe. They were struggling, trying to solve this problem, and they never solved it. They were making experiment after experiment, trying to observe macroscopic quantum coherence of this artificial circuit, and they failed. So this really turned out to be very, very difficult. The solution came with this gentleman. It's an amazing physicist. Hans, actually he is Johannes. So if you look for his name, he is J. Moon. movie is beautiful in Dutch. And interestingly, I have a retired colleague in Karlsruhe, famous professor Gerd Schoen, which is a nice German, Schoen, and they were working in the same lab together, Dutch movie and German Schoen, one theorist and one experimentalist. They've done very little. Anyway, Hans came up with the idea of making this double potential very shallow in a very clever way. He suggested not to use the external control, which will be subject to fluctuations due to fluctuating currents, but rather use another Josephson inductance, which will be determined by the area of the junctions. So instead of having now, this is our quantum junction, instead of having now a junction in superconducting loop with particular geometrical inductance, he suggested to make a very small, a very tiny inductance, and to add the inductance to the loop needed value. He suggested to have here two Josephson junctions, which will have critical current larger than the quantum junction. Typically, a quantum junction will have about 70% of the current of the large junctions. And this was really kind of breakthrough. The theoretical paper came in 1999, and they were able to, in Delft, to realize this for the first time with this device, actually 2 years later. You recognize here that this is 3-junction loop. This is a qubit. 1, 2, 3 junctions. These are shadows, which I explained to you. These are basically shadows of electrons, which appear because of shadow operations. So it was like operating aluminum from this side and from this side. And this is a measurement squid. So the squid was galvanically coupled to the qubit. This is a qubit, and this is a measurement squid. And basically, this measurement squid was needed to determine the final state of the qubit in this experiment. So, and it turns out actually that at the degeneracy point, the energy of this state and this state counterclockwise current is the same. And if the barrier is very low, then one should be able to observe the tunneling between the states. One can take now the system in a more rigorous way. One can write now the flux quantization for 3 phases. These are phases phi 1, phi 2, and phi 3. This is our quantum junction here, coefficient alpha 0.7, as I said, roughly. And this is just preferred choice for the height of the barrier. One can make it, of course, 68 or 72. It still works. It's a convenient range for the good frequency stream. And then if you now fix now n to 1 for the flux quantization, the additive, if you fix it, then you could exclude the phi 3 from this this formula, and one can replace now the energy of the third junction. Now the energy of the system is the energy of the first junction, energy of the second junction. This is the Josephson energy of the second junction, and this is the Josephson energy of the top junction, which now contains only phi 1 and phi 2. And this is a kind of potential for which one can normalize the Josephson energy. So it's a denominator here. And if one plots this potential, it looks like this in 2 dimensions. So this is phi 1, this is phi 2. It has some maxima, which are red, and some minima, which are blue. And because the system is symmetric, it's feasible to assume that we move along the diagonal. So these 2 phases are equal. So if you move along the diagonal of this potential, one can recognize this minimum here. But if you look closer, there is a little darker area here and another little darker area there. And if you make a cross section, it looks like this, where this barrier is only in the range of a few microelectron volts. So it's very tiny barriers there. And basically, the key idea was not to produce this by external control of this junction, but rather using the area. Because in this case, it was much more robust with respect to external noise fluctuations. It really worked. Now, a few words about the manipulation. So this flux qubit is very beautiful because, as you remember, we should remember, we started from 2-level systems. When we discuss qubits, we have a 2-level system. You have basically a harmonic potential. So you have states in the left and right. And flux qubit is exactly like that. It's simply a toy model system. Now, the Hamiltonian in the spin operators will look like this. So this is corresponding to tunneling. sigma x, and this is corresponding to the tilt of the potential. And if you calculate the eigenstates, then for half flux quantum, which means this symmetric potential, the energy level separation will be minimal. And then if you change the potential, change magnetic field, you simply change the symmetry of this potential. So you make one well higher, the other one well lower. And it's clear that the energy level separation in this case will increase. So you should know from quantum mechanics, from physics of spin 1/2 system, that the energy level separation delta is the splitting in the symmetric potential. And if you change the epsilon, then the energy level separation is proportional to square root of the delta square plus epsilon square, where epsilon is this axis. So this is a standard kind of separation. Here is a hyperbolic type. All right, so this is a flux qubit. And one can prepare a superposition of the two states, and then one can detune from the symmetric point, and then measure, for example, the probability of the lower energy state. And if one detunes from this state, then the matrix element of tunneling between the two states becomes rather small. This is an advantage for measurement. As you see, these two states, they almost not overlap, and it's kind of natural because this lower energy state, so the lowest energy correspond to this state, and the first excited state will be that one. It will be more localized to the left potential. And basically, this is allowed also for doing the projective measurements, as I explained before, on this type of system. Now, this is a full solution of the Hamiltonian of the system. I probably will not discuss that. Of course, there are also high energy states. This is half-flux quantum. These are the two lowest energy states which I discussed. Separation between them will go this hyperbolically as a function of flux, but there will be also high states. But those high states we don't pay attention because we don't excite them. They're at very high energy, and the radiation which we apply is non-resonant with those levels. So basically, we can work really very dedicated just with the lowest energy states. Now, this is a silver qubit which turned out to work around the year 2000. I think they measured the spectrum in 2000, and then the first paper where they measured constellations was 2002. And then the question was how to make really the coupling between the qubits. So remember that to do quantum computing, you need to be able not only operate one qubit, but you need to couple qubits together and also manipulate them and switch on and off the coupling. And this work actually was done in the group of John Clark. I was happy to be there as my sabbatical at the time. And the idea was the following. So suppose we now have one flux qubit here and then another flux qubit there. And I just explained to you how this one works and this one works in the same fashion. But now what we want to have the coupling between them not only achieved by inductive interaction, but also we want to make it tunable. We want to switch the coupling on and off. And the idea was the following. So there is always, of course, the coupling due to the stray magnetic flux between the two qubits, and this mutual inductance is negative. Mutual inductance between two loops nearby. Now, if you enclose this in a superconducting loop with two Josephson junctions, this is again in the squid, but these are just bigger junctions here. Then each qubit is inductively coupled to that loop. So if you send the current here in this qubit, then there will be opposite current generated in the squid. So this will be negative coupling to the squid, and then it will be also negative coupling between this squid and another qubit. So totally, the coupling through the squid is going to be positive, and coupling through the direct coupling is going to be negative. And then, by changing the current in the squid, one can tune these two inductances in a continuous way. And one can basically cancel the coupling completely because one can make the coupling to the squid being exactly equal to the coupling which is achieved here directly. And this was done in this experiment at the time. So when you basically look into the spectrum of first qubit and the spectrum of the second qubit, these are these hyperbolas, epsilon square plus delta square and the square root. There is a point where the frequencies of the two qubits are identical in this flux. And as you know, if you have two quantum systems, which interact and have the same frequency, then of course this interaction leads to the, as English literature tells, lifting degeneracy. Снимается вырождение. Если у вас есть два квантовых состояния, имеющие одинаковую энергию, между этими компонентами есть взаимодействие, то вырождение снимается, возникает расщепление, возникает щель. И нижнее состояние, это, соответственно, есть симметричная суперпозиция двух, а это антисимметричная суперпозиция двух. Есть та же самая история. And then here you see that actually at zero current of the sphere there was an interaction in the range of actually about 100 megahertz. And then by tuning the current in the script, going higher and higher, this gap was shrinking and then collapsed. And then if you measure this gap as a function of flux, these are points of measurements, exactly at the current about 0.6 microamp, the coupling was made zero. And basically this is the point where the coupling actually changes from being positive to being negative. So this experiment actually demonstrated for the first time the possibility of making coupled flux qubits, and moreover with controlled coupling. And this was really done like this curve was usually the whole night of measurements. The next night you measure this one because you need to do a lot of averaging. And what we observe now about the tools which are being used for measurements of qubits is really amazing. It's completely changed the world. One can now do these experiments in milliseconds, basically. All the tools available these days. Anyway, once we have coupled qubits, we could make quantum gates, and this was done shortly after that paper in the group of Hans Mu in Delft. So they came up with the idea of using two inductively coupled splits in this gravimetric qubit. Basically, this gain is flux qubit, but it's not being like one loop with three junctions. It's actually a figure of 8 loop with three junctions. And if you track flux quantum here, then this loop will be in a superposition of the states flux quantum here, flux quantum there. Flux quantum will basically tunnel from this quantum junction. And this makes the whole system kind of protected. And you could get the flux quantum there by cooling down to low temperatures from room temperature. And skipping the details, I just tell that the CNOT gate is described like this matrix, and this is the first measurements of that. You recognize here matrix elements, that one, these two, and those two. The fidelity was very limited, but nevertheless, it started to work, and this was already very, very promising. This is in the same paper, and I think we'll talk about quantum gates later on. The time is over today, so I'll stop here. Maybe I'll tell you a little more next time about that, but not really details. Any questions? For those of you who don't know, superconductivity can be difficult to understand. So I really recommend you to read this book to understand the Johnson effect and the other understand the book. For those who have superconductivity, if you feel like it's tough, remember atomic physics, remember radio oscillations, remember all that, refresh this. Because when we go to the gates to more complicated circuits, it's going to be really tough material. So it's going to be more and more detailed and sophisticated once we the course. So if you want to stay on board, you need to do something in the meantime. So I welcome you to try that. Окей? На сегодня все. Если есть вопросы, подходите. Так увидимся через неделю.